All right. What we are live. Lecture 5. So lecture 5 is all about molecules, all about covalent bonding. I am going to start with one or two little comments though. I've been reading through the labs that you submitted. And there were two comments that I wanted to make. One is a personal pet peeve, and the other is a more general statement. So, oftentimes when people type out numbers with units, they'll type it like this. Always make sure that between your number and your unit is a space. Make sure there's an empty space. I will, for this one, I think I let you get away with it. Future labs, I'll return it to you and make you put in that empty space. It's just a personal pet peeve. Number, space, units. When you're talking about precision, make sure you reference the class data. If you have one data point, like from your experiment, some of you did multiple runs, and that was great. But if you only did one run and you said the beaker is the least precise, well, you can't tell that from one run. You need multiple runs. So you actually had to reference in your lab the class data. Okay. All right. So that's just a little heads up about the lab. This one's just Mr. Bennett's pet peeve. All right. So we're going to talk about covalent bonding. You are going to get, this is G block. G block will get the first part live. F block will get the second part live. And I forget another group will just get one short little lesson on organic chemistry. So covalent bonding makes molecules. Molecular compounds have different shapes and can be polar or nonpolar. Molecules are much more interesting than, to me, and to Mr. Hamill, than ionic compounds or metals. You can have so much more diversity. You can have enormous molecules that have tens of thousands of atoms all covalently bonded together. Or you can have things like oxygen, which are just two oxygen atoms bonded together. So there's a lot of diversity in it. And as such, there's a lot of really interesting things. So we're really going to focus on shapes and polarity in this unit. So we will go to things you should know from the story of chem. Just to remind you, this is things. Oh, you're not going to be able to read that at all. You should know that. You know what? Let's just take that out. All right. Things you should know from the story of chem. So, chapter 5.1.1. Covalent bonding can be described by drawing Lewis dot structures for molecules. You need to be able to draw Lewis structures well in this course. Not only will it help you in this course, but when you take organic chemistry in college, if you're really good at drawing Lewis structures, you're a step ahead. Covalent bonds can be single, double, or triple, and atoms and molecules usually follow the octet rule with some exceptions. So let's start with Lewis structures. You see I have like all my notes already. For those of you who are watching live, you can see I do all my notes out. Mr. Hamill just does it off the top, but I make sure I have to have everything all organized. So Lewis structures help us understand the bonding, the covalent bonding in a molecule. So really it's a model. I don't need to write really. It's a model for molecules. This will help us determine shape and eventually polarity. So the basics of a Lewis dot structure are starting with an element and their number of valence electrons. So Lewis dot symbol Lewis dot symbol for something like fluorine would just have the number of valence electrons around it. 1, 2, 3, 4, 5, 6, 7. Now, and I do it intentionally in that order because if I write it 1, 2, 3, 4, 5, 6, 7, I can tell how many bonds are left, or how many bonds need to get made to fill up the octet. Whereas if I do it with oxygen and I just went 1, 2, 3, 4, 5, 6, it's harder for me to see that oxygen wants to make 2 bonds. So what I do is that. So I know I have a lonely electron here and a lonely electron here. So neon 1, 2, 3, 4, 5, 6, 7, 8. I will say this, I have looked at some of the tests, and a lot of people still use magic. Like, neon is especially stable because it has a full octet. You need to explain more deeply what makes it stable, right? Yeah. No, so this is, I took that out to show you that this allows you to see how many bonds oxygen wants to make. And you know, lonely electrons want to bond in nonmetals. So you start with these Lewis dot symbols, and then eventually you build Lewis dot structures. So symbols are for individual atoms of an element. Symbols are for putting multiple, structures are for putting multiple atoms together. So I'm going to try to judge when you guys are done taking the slide of notes. If I'm wrong, you just yell at me, okay? Just say, stop! Ooh, I'm sorry, those of you at home who are watching or listening. That probably was very obnoxious. Okay. So here's an example. Oxygen. So I'm gonna do this 2 ways. 2 ways. There's the way that is sort of easiest for me to see, and then there's the way that will probably be easiest in the long term. So I start with my 2 oxygen symbols. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I can see now that each oxygen has 2 lonely electrons, and they want to pair up. So what I do is I connect my lonely electrons, and I get oxygen. Oops. Now, here, shared electrons, which basically represent a covalent bond, are represented by a line. So I'm not sure this is particularly new to most of you. I think most of you have seen this before, but let's just remember remember our basics. Whoops, sorry. I did not mean to do that. So that's the visual way. The next way is called the count and check method. How many of you guys are familiar with the count and check method? About half, maybe. Okay. So in the count and check method, step 1, count total valence electrons. So I have 2 oxygen atoms. 2 oxygen atoms. Each one brings 6 valence electrons to the table. So I'm left with 12. Step 2. Place atoms with single bond and full octets. So here's what I'll do. Single bond. Those look like eyeglasses. Full octet. So now, after I've placed my atoms out there with a single bond and a full octet, I count how many I put out. So 2, 4, 6, 8, 10, 12, and the bond is also 2. So I put out 14. Check. Does 14 equal 12? Obviously not. So this structure cannot be right. So if you have too many electrons, your next step is to make more bonds, and then you'll repeat until numbers are equal. So what do I mean by this? Well, when I make a double bond, it just means that the atoms are now sharing more electrons. So in the case of O, or specifically in the case of O2, instead of each having a lone pair, I'm actually just going to put another bond in the middle. So does each oxygen have a full octet here? Well, let's count. All right, 1, 2, 3, 4, 5, 6, 7, 8. This oxygen's good. 1, 2, 3, 4, 5, 6, 7, 8. Each oxygen has its full octet. I recount how many electrons did I put out? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 electrons. Now, the count and check way is more complicated than the visual way. But when we get to really complicated molecules, this is the way, the count and check way is the way you're going to want to do it. And we're going to practice this. Practice makes perfect with Lewis structures. We're going to be doing lots and lots of Lewis structures. All right. Nitrogen. This one I'm just going to do the count and check way. So step 1, I know each nitrogen has how many valence electrons? Raising our hand. Raising our hands. Yeah. 5. How did you know that? Yeah, you look at the group number on the periodic table. So N2 has 10 valence electrons to work with. All right, so step 2 we're going to put over here. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, so full octets. Now I count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That is a sad face. I don't know, is that sad or anger? I don't know. So I know I have 4 too many electrons. So you'll get to the point where if you have 2 too many electrons, you make 1 double bond. What if you have 4 too many electrons? You either need to make 2 double bonds or 1 triple bond. So we know that's no good. Let's see what happens if I make a triple bond. Redo. All right. So check each octet. The left-hand N has 1, 2, 3, 4, 5, 6, 7, 8. Remember, each line represents 2 electrons because that's a bonded pair. And on the right has 1, 2, 3, 4, 5, 6, 7, 8. Octets check. 10 equals 10. And we are happy. So there is some level of iteration involved in doing Lewis structures if you do the count and check way. All right. So we've now seen double and triple bonds. We've done very simple Lewis structures. Now, how are these bonds different? Oh. how do single, double, and triple bonds differ? Before we delve further into Lewis structures, think of our fundamentals. Specifically, Coulomb's law. All right, so in a single bond, an example would be hydrogen. How many electrons are shared? In a single bond, how many electrons are shared? 2. 2 electrons shared. Then in a double bond, of which we have the example of O2, 4 electrons are shared. And in the triple bond of nitrogen, 6 electrons are shared. So we're sharing more electrons each time. And so that increase in the sharing of electrons is going to inform the 2 characteristics of bonds that you're going to need to know about in terms of single, double, and triple. All right, we can turn the page. So we're not going to get into the ways that we measure bond length. There's a couple of different ways. It's really esoteric to me. It's strange. But we can measure a single bond in fluorine as 142 picometers. Double bond in oxygen is 121. And a triple bond in nitrogen is 110. Now, why did I choose these 3 elements, do you think? Edward? They're all in the same period, right? This trend would not be perfect if I chose elements in a different period because our atoms would be larger or smaller. But in the same period, what can we conclude? Yeah. Yep. More bonds. I'm just going to more bonds equal smaller bond length. So let's go back. If we go back to our fundamentals, we can understand this using Coulomb's law. Greater magnitude of charge equals greater attractive force. So remember, you can memorize these trends. That's fine. But I would love it if you could understand it in terms of the fundamentals. So it makes sense that the N2 bond is smaller than the O2 bond, because in N2 they have 6 electrons that those two nuclei are fighting over. The nuclei aren't just attracted to 2, they're attracted to 6, right? So greater magnitude of charge means they're going to be pulling more tightly, which means they're going to be stuck together more closely. Right. So you need to know that double bonds are smaller than single bonds. Triple bonds are smaller than double bonds, or shorter, I should say. All right, and then bond strength. Remember, it takes energy to break bonds. We're going to hammer that one home over and over and over and over and over. We say like, oh, food is stored chemical energy, so breaking those bonds must mean breaking bonds releases energy. No. When you eat food, you're breaking weak bonds and making stronger ones. So you're putting some energy in to break the weak bonds, But the fact that you're making these really strong bonds is where you get the energy from. So breaking bonds is always endothermic. All right. So if I wanted to break a mole of CC single bonds, it would take about 350 kilojoules of energy. It takes about 600 kilojoules to break 1 mole of CC double bonds and 835 kilojoules to break 1 mole of CC triple bonds. Now you notice that that's not a linear progression, right? It jumps from 350 to an extra 250 and then an extra 235. We're going to get into how these are actually aligned when we talk about the orbitals, but what you need to take away is it takes much more energy to break a triple bond than a double bond and a double bond than a single bond. So, whoops. And this sort of makes sense, right? More bonds equals more energy to break. So the extra, and I wanted to mention the extra pull from the nucleus outweighs something. What else is going to happen if you start shoving more electrons in between? Yeah, you're going to get some repulsion between the electrons, but the extra pull from the nucleus outweighs the repulsion from closer electrons. And there's also some of that has to do with the arrangement of how the electrons are in space, but in general you would think, oh, more electrons closer together means higher potential energy, means it would be easier to break, but the extra added strength of those two nuclei fighting over the more electrons holds it closer together, means it'll take more energy to split apart. All right. Any questions about bond strength and bond length? All right. Let's all stretch for a second. This is rough. I'm not used to lecturing like this. Oh. Does anybody want me to draw a picture of something on here? What should I draw? Happy face? All right. Oh, I heard self-portrait. Oh, wow. It has to be good. Yeah, no, that's... I sometimes get these like wings that go up on the side. It makes me look a little devilish. All right. I'm always smiling, or at least I'm trying to. There we go. That's actually one of my best self-portraits that I think I've ever drawn. All right. We ready to move on? Dr. G, this isn't what we do in AP Chem all the time, draw self-portraits. Yeah. Okay. So Dr. G just walked in. So I wanted to assure her that this isn't all we do. Okay. So polyatomic Lewis structures. I introduced Lewis structures very quickly with diatomic things. Oxygen, nitrogen, O2, N2. But now we're going to go into a little more depth with polyatomic Lewis structures. So NH3. Do this at your desks. Let's see if you remember NH3. Dr. G loves Lewis structures. We love Lewis structures too. No problem. Okay. I'm sort of walking around. If you're captioning this, you don't need to put this part in. Oh, I even see some people who are jumping ahead and putting it in sort of 3D shape. Interesting. Okay. So for NH3, as I walked around, you always want to make sure you put the one that bonds the most, in the middle. So N, we know H can only make one bond. So H can't be in the middle of anything. Neither can F, Cl, Br, I. They can never, well, I shouldn't say that. Br and I can. F and Cl can't. So N, H, we put them out, we make our single bonds, we fill our octets. Oh, wait. Do I need to put octet in for hydrogen? No, no. Hydrogen, you can only get 2 electrons on that first energy level. If you tried to add a third electron to hydrogen's valence level, it would jump to the second level. Sorry, if you tried to add a third electron to hydrogen, it would jump to the next energy level, which would be really, really far away. And so the hydrogen nucleus couldn't pull on it, right? So it's not that necessarily that the filling the shell is the magic. It's that if you tried to add another one, it's so much further away, and the nucleus can't hold on to it, right? So NH3. CCl4. Give it a go. All right, so again, it's cool that I see some people jumping into the 3D structure. We're not quite there yet, although we'll get there. So here, if we want to do count and check for CCl4, and yes, Mr. Hamill is making fun of me for the way I look in the Madonna mic. So I don't know who that's a diss on. So let's put them out, single bond each. But here, this is a little more complicated because we have 4 valence electrons from carbon and 4 times 7, 28 from chlorine. So we have a total of 32 valence electrons. So let's put out our octets. Oops. All right. Whew. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, maybe. 26, 28, 30, 32. Check. Yay. We did it. All right. Yes. Oh, does it like this one? Okay, the question was, so since this is your first live lecture, it's really difficult if you're watching at home when someone asks a question, right? So I'm always going to try to repeat the question that's asked, so remind me if I don't. So the question was, does it matter where this hydrogen is placed? And it doesn't. You can put it on the top or the bottom as long as you have the 3 hydrogens with single bonds and the 1 lone pair. You're fine. All right. So try the next 2. We're going to start expanding beyond single bonds. So I know these are ones that most of you have seen before. All right. So carbon dioxide, we put carbon in the middle. That's the one that wants to bond the most. Oh, whoops, I jumped ahead. All right. So if I fill the octets, well, I know CO2, I can have 20 valence electrons. If I fill the octets, I have 2, 4, 6, 8, 10, 12, 14, 16, 18. Wait. What did I do wrong? Oh, it's only 16. Thanks, math. All right. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Well, I have 20 valence electrons out there right now. So I have 4 too many. Each time you make a double bond, it drops by 2. So I know I need either a triple bond, probably not going to work, or 2 double bonds. So if I do that, C, O, 2, 4, 6, 8, 10, 12, 14, 16. Yay. Now, I could draw it like this. Here's the problem with the count and check method, is that there might be multiple ways you could draw it. Because you could draw it like this. Does that fit our criteria? Does everything have an octet? Does it add up to 16 valence electrons? Now, why is this wrong? We'll get to why it's wrong. That was sort of a rhetorical question. All right. We're gonna have ways of determining why things are wrong. So be careful with the count and check. All right. Now HCN, I'm not going to go through the whole process again, but you should have gotten this. You know hydrogen can't make more than one bond, so that can't be involved in the double bond. You know that you have too many valence electrons, because here you have 1, 5, so that's 6. You only have 10 valence electrons to work with. Yeah. So the question was, does lone pair placement matter? It's a good question. When you are doing Lewis dots, no. When we start getting into shapes, it'll matter a little bit more. But for now, we don't care where you put it. I just put the one for nitrogen there because that's actually where it would be if we did the 3D shape. But if you put it on the top or on the side, totally fine. No. All right. So these are like your basic Lewis structures. Now, we get to a weird one. CO. Oops. What is CO? Carbon monoxide. What is carbon monoxide? Where does it come from? Edward, do you know? It comes from exhaust, and it's a poisonous, odorless, colorless gas. So, yeah, Alexi. Yeah, that's actually, those were the exact words that I was about to use. It comes from the incomplete combustion of fuel, right? So we learn in chemistry, like in your high school chemistry, Chem 1, Honors Chem, AP, we learn, oh, things burn and it makes carbon dioxide and water. That's true for the most part. But if that's only 99.9% true, that other 0.1% is other stuff. So it doesn't perfectly form CO2. Some level of carbon monoxide is formed. All right. And carbon monoxide is really bad because it binds to, I think it binds to your hemoglobin. I'm not 100% sure. Yeah. And so instead of transporting oxygen around your body, that's what gets transported around your body, and that doesn't help you. So yeah, it's a very toxic gas. And like a lot of toxic gases, has no smell. So you probably have carbon monoxide monitors in your house. If not, you should make sure you have one. Okay. So let's do the visual way. Carbon, 4 valence electrons. Oxygen, 6 valence electrons. All right, so we know oxygen wants to bond 2 times. So let's match that up. Match it up. Oh, crap. Carbon still has 2 unpaired electrons. And oxygen's already filled up. Huh. This is a problem. Well, let's try the count and check method. So if we do count and check, well, I know I have 4 valence electrons from carbon and 6 from oxygen. I have 10 valence electrons to work with. So if I put it out like this, fill up the octets, I count. That gives me 14. So can't have that. Well, I know if I have 4 too many, then that means I need 2 double bonds, which is impossible here because I only have 2 atoms, or a triple bond. So, no, it doesn't work. Fixed. Okay, so boom, 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 boom. Oh, okay, so now this one gives me 10. Oops. Ugly. 10 electrons. This works, but I don't know if you remember from chemistry, your honors chem or ACP chem, oxygen only wants to bond twice. But here, O has 3 bonds. That's a mystery. So our count and check method worked, but visually that doesn't make much sense. Well, you're not going to have to wait long for the solution to the mystery. All right. If you look on the next slide, we can explain molecules like carbon monoxide. Carbon monoxide is a quite stable molecule. So there's 2 ways that we're going to, well, 2 ways to explain it. One way is the classical way, which is what I learned when I was doing organic chemistry in college. And then there's the modern way, which is, so the old school way you might hear is a coordinate covalent bond. I'll explain on the next couple slides. The modern way that you're going to be, don't need to know. Don't need to know, but you'll hear it. You'll hear it in future classes, like college classes. And then here, this is very important. All right. So you need to be able to do formal charge. So what are these 2 things? So we can describe carbon monoxide with coordinate covalent bonds. So, like in the case we had a moment ago, so if we start with this, right? Carbon and oxygen form their double bond. That is what they traditionally will form, a single or double bond. But carbon's octet isn't full. Oxygen's octet is full. Well, carbon has a relatively strong nucleus. So any electrons in its vicinity that, if it has vacancies in that second energy level, it'll try to pull them closer, right? The strong nucleus that can still pull on electrons in its valence energy level. So what actually happens is we describe it as this. The electrons, the lone pair from oxygen, becomes a bonded pair. And the way you'll see that drawn is this. So the coordinate covalent bond is represented by an arrow or a half arrow. So you can think of it as that, like, that lone pair is moving towards the middle. So the arrow is in the direction of electron movement. Okay, so that describes it. Unfortunately, that's not going to be super helpful for us moving forward. What's going to help us much more moving forward is understanding formal charge. I'll give people a few seconds to get this done. What time are we finished? 45. This 45. So I had some honest answers and some not so honest answers. I thought it was 45. Yeah. All right. So let's do formal charge. What is formal charge? We can assign individual charges to each atom in a molecule. So this helps us understand stability, which we'll get to in a little bit. Okay. So how do we calculate formal charge? And what does that look like? Well, formal charge is equal to the number of valence electrons in a neutral atom. So that would just be like for carbon, it would be 4. For oxygen, it would be 6. For fluorine, it would be 7. Number of valence electrons. From that, you subtract non-bonding electrons. And then you also subtract number of bonds. And that's what allows you to find the formal charge on any atom in a molecule. So I'm going to call this formal charge. And the formal charge is almost always 0. But note that I said almost. Yeah. So the question was the non-bonding electrons. Yes, those are the electrons in lone pairs. Yep, exactly. Okay, so now let's look at carbon monoxide again. In a minute, I still see writing. Yeah. Good question. You will see this written in a. I like to just the number of bonds, or you'll more frequently see it written as bonded electrons divided by 2. Oh, the question was for number of bonds, is it actually the number of electrons in the bonds or the number of bonds themselves? So it's the actual number of bonds, but in the textbook, and if you guys ever want a textbook, you can just let me know, but almost nobody finds it useful. But if you're someone who learns well from textbooks, I don't know if I ever threw that out there. Bonded electrons minus 2 or number of bonds. It gives you the same value. That's a good question. Are you doing a little manifest destiny on taking over the foot space? All right. All right. So, describing carbon monoxide with formal charge. So let's go back to our Lewis structure. Well, and let's calculate the oxygen formal charge. So, oxygen's in group 6. It brings 6 valence electrons to the table. It has 2 electrons. It has 1 lone pair, which is 2 electrons. And it has 1, 2, 3 bonds. So its formal charge is +1. So you would just write a plus over the oxygen. Now I want you guys to figure out the formal charge on carbon. So the question is, and it's a very good one, are these the same as partial charges? They're not the same as partial charges. Partial charges, which we'll get to later in this chapter, these are denoted by the lowercase Greek delta. These we just put in circles above. So this is more of a bookkeeping method for us. This is an actual, like, denotes the actual positive and actual negative sides of a bond or a molecule. All right, what did we get for carbon? Just somebody shout out. -1. Good. So we have carbon brings 4 to the table. It's got 2 electrons in lone pairs. It has 3 bonds. So it is -1. So we would put a little minus above this. So instead of using the coordinate covalent bonds, we can say, oh, oxygen just has a plus formal charge. Carbon has a minus formal charge. All right. It's a long time for me to be standing up here talking. How you guys doing? I see some people fading. It's getting to be lunch. Okay, for it. A drawing request? All right. Superman fighting Batman. I don't know that I'm quite good enough to do that at this point, although if I practiced enough. Although I do oftentimes just, if I need to doodle, I'll doodle, that. A little bit more, a little bit better than that. But, so I could do... That looks... Ouch. Batman is just a blob, a sphere, and Superman's kicking his butt because Superman's the best. Oh, yeah, they've definitely... See, I even did the spit curl. Oh, they've fought on multiple occasions. I'm sure they will in 2016 when Batman vs. Superman comes out. Yes, he does. He does. All right. But if you're Superman, oh wow, we're getting into this discussion. If you're Superman, you just stay far away from Batman, even if Batman has kryptonite, and you just zap him with your heat vision. What's right. Yeah. And Superman could see or hear or whatever. So yeah, yeah. But Superman has parent issues too. All right. Okay, I can't believe this is being recorded. So whoever captions this can choose whether or not they want to keep this in or not. But there's been a long diversion on Superman versus Batman. All right. So an easy mnemonic is honk 1 2 3 4. Yes, it's ridiculous, but it'll help you remember hydrogen, oxygen, nitrogen, carbon, and the number of bonds that it normally forms. 1, 2, 3, 4. Look at that. Honk. 1 2 3 4. So, of course, we tell you this after an example where oxygen bonded 3 times. But nevertheless, this is a general rule that works almost all of the time. So just, this will help you draw Lewis structures, but make sure that you can understand what's actually going on. Okay, so I would like you guys to try to do the next Lewis structure. Now, O3, how are we going to draw ozone? Try it. All right, so I walked around a little bit. The most commonly done incorrect version, which actually, so if you do the count and check, here's the problem with the count and check. You can get things like this that are not true. Somebody shout out a color. I heard blue first. So a lot of people do this for oxygen. So works with count and check, but not true. Not with oxygen. You can do it with carbon. You can't do it with oxygen. You can get that little triangle. You can do a triangle too. I'll show you at some other. Don't worry about it. Not important for right now. So the other option you had is this. This is the other way you could have done it, using the count and check method. Now this one looks nicer, right? I mean, it's cool. It's a triangle. But why is this one messy? Ben, yeah, go ahead. It doesn't look right. It doesn't look right. Yes, it is aesthetically displeasing. Yes. Yeah, how do you know where the double bond is? Like, how do you decide? Now, you can do formal charges. So we can put in formal charges here. If we do that, this is going to be minus, and this is going to be plus, right? But that's still not helping us. So we need to learn about a new concept. And it'll be the last thing we do before class ends. So what scientists did was they realized the limitations in the Lewis dot because they actually measured the bond length in ozone. Oh, by the why is ozone important? I want to hear new voices if I can. I've heard. Let's get somebody who hasn't talked today. Might know why ozone is important. Yeah, Carter. All right, so it's in our atmosphere. It it doesn't necessarily hold the heat into our Earth. Those are the greenhouse gases. It's at the top layer. We had a big hole form in it, like in the 80s, 70s, 80s. That's it. It blocks UV. So the ozone layer blocks UV. And actually what happens is UV light hits ozone, and it breaks off one of the oxygens, and it protects us from getting UV and skin cancer. Yeah. So the question was what forms the ozone? There's a reaction. I think this is catalyzed by chlorine, like chlorine-free radicals. But there's a reaction that takes place in the upper atmosphere in which ozone replenishes itself. Or no, chlorine breaks it down. There is the chlorofluoro, yeah. Chlorine breaks it down, which is why it was a problem. There is some sort of regeneration process. Luckily for us, ozone doesn't hang out down here because ozone is really toxic. You would think like, oh, maybe it's extra awesome for us because it's 3 oxygens instead of 2. Yay! No, it'll kill you. Ozone will kill you very, very quickly. It's pretty toxic. So, chlorofluorocarbons, which we used to use for refrigerants, and for aerosol sprays, were being put up into the upper atmosphere. It was breaking the ozone down, and you have like these big holes in the ozone layer, which allows UV light to come in, which gives us skin cancer and all these terrible things. So that's actually one case where we really suck at stopping global warming. We really suck at it as humanity. But we did a great job with chlorofluorocarbons, getting rid of them. The ozone hole is growing back. It's actually replenishing. So, there's still hope for us with global warming, but I'm less optimistic. Okay, so the structure of O3 as expected from our expected Lewis structure. Well, here's our expected Lewis structure. So we would expect that there is an oxygen with 1 short bond and 1 long bond. Right? We learned earlier in this lesson that double bonds are shorter because there's more electrons in the middle. There's more attraction between the nuclei and the 4 shared electrons than there is the nuclei and the 2. This is a little bit overdramatic. But when they actually study ozone, they find that there are 2 bonds of equal length. So there isn't 1 double bond and 1 single bond. There are 2 bonds that are of equal length. And I'm just going to note that this is not to scale. And with that, we will stop.